Okay, so what we were doing last time, and I ran out of time as usual, Aaron Fest, and any name, if I see that and I say Aaron, that's obviously an Irish, I don't know if that person's Irish, I'm pretty sure that's Irish, because Ireland in Irish is ear, so that looks to me like a very Irish name. I have to look it up. So this is more time-dependent Heisenberg operators, and we're going to do a more general case. So remember that we did a free particle, so that the Hamiltonian, which is part of the Heisenberg equation of motion, was just p squared over 2m. And you're doing the same thing. So I kind of did questions 1 through 3. I kind of mostly did them in class. Okay. And then on questions 4 through 6, you actually have a potential energy. And so that really complicates things. In fact, it's so bad, I did export it for you in the appendix, because that was pages and pages of stuff. And that was done with an equation editor. And I kind of know what to do, because I have an answer key. So what happens when you have even more complex potential, or the potential is multidimensional? So that's what we want to do with this. Is I'm going to write down the Hamiltonian in a general case, and of course, no, you're not going to have some weirdness with p squared over 2m, and assume that the potential operator is really masking a representative for the position operator. Because potential energy is usually just, x squared, right? So that's like a bond, that's a harmonic oscillator potential. Anyway, so there's anything you might think of can be generalized to say the potential energy is just a function of position. Okay, but I'm not saying what it is. And the point of this, especially as you do questions 1 through 3, then you do 4 to 6, is that if this gets more complicated, then everything gets more complicated in a big way, right? These things have a way of exploding on you. Okay, and again, let's review what it means. So I've got an operator, I'm doing the Heisenberg, I'm doing a bunch of redundancies, I'm giving it a little h, I'm putting parenthesis t to remind you that this is the time evolving one. Here's the thing we derived in class, not that you really need that. And the operator is equal to itself, which again is hideous. You have a diffie-q to solve an operator, but we have tricks, of course. I wouldn't, if this was a hopeless process, of course, we wouldn't bother. Now, remember that you can make the Hamiltonian time dependent. Recall that? So I'm doing another trick here. I've decided to make the Hamiltonian time dependent. It's equal to its time independent form. So I put HH, that's kind of awkward, isn't it? But I'm going to write the Hamiltonian in the time dependent form. And you'll see why in a minute. But we'll assume that the position operator is not time dependent. And the reason I'm doing this is hopefully you realize you can just immediately cut that out. It's going to commute. So I've done a bunch of tricks here. If you recall how I derived the Heisenberg equation of motion, the Hamiltonian was technically time dependent as well as the operator itself, which is the same as the operator here. Again, this actually, unfortunately, makes it way more complicated than we would like. But I got rid of the time-dependent Hamiltonian because it commutes with the time evolution operator. Here I put it back, and I did that so that I could just, again, if you write out this commutator, you can see immediately that this part doesn't do anything. Okay, so what you end up with, and I'm still just repeating what I did last time, what you end up with is this, and I've got no tricks here for this time-evolving momentum operator. I don't know why I'm writing this so small. I can't see it back there. I don't know if you can see it on the video, but anyway, you should know what it is. Okay, so I've got this. All right, Now the trick is where I guess that this is an approximation. I did get a chance to look. I tried looking this up before. I needed to do it again. This is a theorem. It's not a law. So I know that there's some ideas that this could the final result is considered somewhat questionable. And I even said why last time, but I'll reiterate that in a minute. And that comes about because what I'm doing here is I am using that Poisson bracket. Now remember, the Poisson bracket is the classical deal. Let me write all that. Hopefully you haven't completely forgotten this. We had a big homework problem on it. Solved a couple of differential equations, so your math skills are good. So I appreciate that. Remember, no operator, right? This is classical. There's no operators don't exist in Newton's world. Sorry about that. Okay, so remember that Poisson brackets were derived, by Poisson, a bunch of those old geezers that you read about. And it's great for solid. It's called the principle of least action. It's just a way of solving Newton's equations of motion. It's really great when you have super complicated stuff. It's just the mathematical way to do that. So, people figured out that the Poisson bracket times IH bar usually equal quantum mechanical commutators. Just seems to work out that way. So this is what we do. Okay, so now let's solve the Poisson bracket. So recall that it's dx dp minus dp dx. Okay, now this is actually already 0. And you may recall, now you've seen this before, it's because of that right there. I'll write that down in a second. Okay, then you permute, so it kind of looks like a commutator, except that it's a derivative. Well, I mean, it's right in front of you, right? So, okay. Now, it turns out that momentum and position have nothing to do with each other, which is kind of weird to me. I mean, remember, we're back in the land of a ball rolls down a hill, which certainly I think anyone can understand. You know, the ball is on the side of the hill. I think its momentum is increasing. So I've always been a little bit confused why momentum has nothing to do with position. But, you know, for the reasons I just said. But apparently that's true. Momentum and position have nothing to do with each other. So that's gone. Remember, the idea of momentum being the derivative of position is a quantum mechanical thing, but we're not doing that right now. Okay, that's 0. Now dp is 1. So, and I've already seen something that looks, that's the force, right? Hopefully you recall some of your freshman physics 1 mechanics. Force is ma is equal to the minus the derivative of the position. Now you notice I said derivative of the position. I didn't say whether it was the time or time or space, did I? But now you should immediately assume that it's space because we're doing things that all of our Hamiltonians we're assuming are actually time independent. If Hamiltonians were time independent, remember all this stuff we've been doing, none of it would be applicable. We have to use that Dyson series. That was the first thing I had to write. The thing that went across the board like twice. Okay, so again, it's the kind of games people play in seminars. It's the derivative of the potential, and then you're like, well, derivative with respect to what? And hopefully you would also have enough forces to know it can only be position because that's the only thing that the potential is the derivative of. It wouldn't make sense to take a time derivative of this because that would just automatically be 0. Anyway, just ramble. Let's see. Okay, so therefore, let me remind you what we're doing. I forgot. Okay, we're still solving the Heisenberg equation of motion, and you end up with a over IH bar minus IH bar That's here. The minus is from here. Well, tell you, no, that's stupid. That's stupid. Let me. Okay, so IH bar is there. IH bar, the other one, is from there. And then I'll do this minus. Okay, we're back in quantum mechanics, so I'm gonna do that. This bracket is just, I'm just trying to make sure you don't think that that's a subtraction. You know, that's one thing that's really a pain is, you can see how this looks like I8, like 1 minus dV dx. It's not, it's times minus dV dx. Kind of surprising that that doesn't cause more problems. Okay. All right, now this next part is, this is going to be a little bit making your eyes cross because I'm going to do the two derivations of once thing. I'm still trying to derive this, but I'm going to have to stop for a second. As you can imagine, as you saw in the lectures, as you're doing on your homework, this coupled differential equation thing that we run into a lot, and this is why I actually introduced it early into the class, is as I go further with this, guess what? There's going to be an x of t. So that's going to pop up. So you may recall that when we did dp dt and dx of t, that they had codependence. So anticipating that, I'm just going to go ahead and do this. So again, I'm going off in a different direction. And that's kind of better, so I'm going to go H, and I'm going to go T. Again, I hope that's, stupid redundant at this point. Now the Hamiltonian will be, and I could write that as time dependent or not time dependent. And as you can see, it's not actually going to matter. Well, I'll write it as time dependent. Okay. Like before, the momentums get wiped out. Here, the potentials will get wiped out. Okay, let's say we're doing bonds because we actually are doing bonds in Friday. So heads up on that. We're doing Hamiltonian, the Heisenberg equation of motion with x squared, with parabolic bond type potentials. Okay, so if that's like x squared, then this is x cubed minus x cubed, then that's 0. So that part is not going to contribute. Okay, so this ends up being relatively easy. And we've actually already done this, to be blunt, right? So at this point, this would be, I believe this would be the time evolving. See, I told you it gets a little confusing. I'm a little confused what's time evolving and what's not. You really can get lost sometimes. Okay, so when you're doing a more complex Hamiltonian, the position part actually is cool because that part doesn't matter. And kinetic energy is always the same. So it ends up being just B over M. Okay, so with that, now we're ready. We're still working on this way, but what am I going to do? Okay, so I'm going to go ahead and do my double derivative trick. You know that you always see that, right? Whenever you figure out almost all of these systems that we've done with the Heisenberg equations of motion, we always ended up with something like, oh, Sx is equal to Sy, and Sy is equal to Sx. And the trick is always to do a double derivative. And you have to do that with your Poisson bracket. You've seen it a zillion times at this point. Okay, so it's also kind of neat to take the Heisenberg equation of motion for a derivative, right? It's kind of weird. Okay, why am I doing that? Well, for one, I actually already know what that is. It's right there. Okay, now this is going to be like, what? what I'm about to do, but it's really straightforward. So now again, heads up, this part is really straightforward, so straightforward it can get confusing. This is the Heisenberg equation of motion for this. Now we're going to assume mass is constant. Right? That's the same thing. What do you do when you have, okay, 1 over m, what would you do? You'd have 1 over IH bar, a commutator. Now, mass is a constant, so we can actually factor out a commutator. So, yeah, this is that. Well, we actually already solved it. Right? I just the 1 over m is the constant just shows up. Okay, so that's actually it. So now let me put them together so it makes it a little bit more easy to view. As often, I'll put the m over here. There you go. So, what I'm seeing here, well, that was bad. There we go. Okay, so mass. What would you call the double derivative of position? Well, the derivative of position with time is velocity. What's the derivative of velocity with respect to time? Mass times acceleration is equal to force, right? Force, which is minus the derivative of potential again from. I bet you that sounds familiar, but maybe it wasn't in your frontal cortex, right? Okay. So then you want to do quantum mechanical averages, and also generalize. And I'm just repeating your book's your book statement here. But you would have how things change in time. So I'm going to use a del operator, right? Yeah, del for derivative. That's ddx, all right. But if you're doing y or z, or maybe it's ddx plus dy dz, then it's more appropriate to use del. It's less complicated. Okay, now, so there you go. Again, this is kind of considered very important. But what is considered funky about it is that there's no h bar. H bar got, and you can see where it disappeared, right? When we injected this classical equation, albeit multiplied by IH bar, the h bar has disappeared at that point and they never came back. So that implies that it's also basically Newton's equation, right? It's just, it looks like I'm going to integrate psi star x psi over there, and then whatever the operator is here, I'm going to integrate that. There you go. And you can actually heads up on your question 4, 5, 6. You can actually use this to save yourself a couple of steps. Not a lot, but you can save yourself a couple of steps. So remember that that's in Z. That doesn't matter. PZ. Momentum is PZ, space is Z, it doesn't matter. X, PZ, Z. Anyway, just heads up, you can actually check yourself with the error test there. That actually does work out. The other things to note, and we're done with this now, is I see people mention this, and to be blunt, I don't really know what to make of it. And I don't know that it really matters. I mean, I generally follow most talks, and if I don't really get much out of this, then I don't know that it's really important to me. If I don't understand, then it's not important. That sounds terrible. Anyway, and that is the statement. So here's the last comments. Last comments are x at t and x. So that's Schrodinger. The Schrodinger x, which is just x, and the Heisenberg t, time-dependent position, those do not commute, right? So hopefully, you know what I mean when I say they don't commute, it means that it's not equal to 0. You can always calculate a commutator, but if it's 0, they commute. If it's not 0, they don't commute. Okay, people say, oh my God, look at that. I see that in talks. Look at that, they don't commute. I don't really know what the heck that means. I mean, I know what it means not to commute, but it means they don't share a common set of states, right? So what does that mean? I think it's really simple, which is kind of dumb, really. Which is that if you start a wave function here, if you wait enough time, it's out here. So it's just moved away. Now, actually, what it would really do, on a flat potential surface, it would actually spread out to infinity. But I'm just saying, okay, there's a magnetic force that made it move to the right, whatever. So I think this is all that this means. But again, I see people make a big deal out of this, and I was never really quite sure why. I don't know that it helps you solve anything. Another weirdness is, let's do this. Is eigenket of again, this is something that I don't really think means this doesn't mean much. I don't see that this offers me any special insight into quantum mechanics. What's happening is that the reason I bring this up is that it does solidify things in a way that I hope, if anything, it's kind of, I'm just going to tell you some stuff, and if you follow me, then you kind of understand it. But do you really need to know this, or does it help you figure out some big picture thing? Not really. Okay, so the thing is, remember that we solve wave functions, eigenkets, in the Schrodinger frame. We're going to start at t equals 0. I mean, we have to start somewhere. As you have seen, especially maybe more so in your undergrad, and actually we're going to get back into this, we're going to start getting back to solving wave functions. They can be a freaking nightmare sometimes, right? So we're actually going to solve the harmonic oscillator wave function. It's kind of sucky. It's a Diffie cube, right? Diffie cube solving Diffie cubes is kind of sucky. So you usually solve them for the t equals 0 operator, right? The whole point of Heisenberg is once you've done that effort, you let the operators change in time and don't worry about having to figure out what the state is doing. Let it just be what it is at the very beginning. Let your operator change. And you know, as much as some of this is kind of awful, you often end up with relationships that aren't particularly complicated, whereas the wave function is pretty complicated, and if you try to involve it in time, I'd expect it to get really much worse. So, so this is why this is the way to go. Okay, so here's the deal. This guy may have been an eigenket, so I'm going to say it's okay. It was okay with the time, the initial time, the time 0 operator, the operators we've been learning this whole time, up until just the last week. It may be okay with that, but in the future, as soon as time moves forward at all, it's not, right? Especially because of like what I just said up here. This state is no longer an eigenket of this time of moment state. Now, again, my point is, so what? I mean, the answer is so what? You're right, so what? I don't think it really matters, to be honest. Because you're going to do expectation values. You don't need states to be eigenstates of operators to do expectation values. That's why we do expectation values, right? That's why I wrote it out here. It still works. You know, the eigenvalue equation is great because it's so simple, But when you need to figure out what an operator is on a state that's not its eigenstate, then you just do expectation value and you still get a good answer. Okay, so that's just summarizing all that we've learned. Now what's happening here, transpose. Hold on, transpose. Okay. So if you want to know what the eigenket is, and I won't do it, it's stupid. There's a little proof, it's in your book. Technically, the transpose operating on the ket is the eigenstate. Now, a couple things here, and again, maybe some good reminders of what's what. Transposes aren't meant to act on kets, they're meant to act on bras. But practically, remember that the transpose of the time resolution operator is plus I h bar t over h bar. I Hamiltonian t over h bar. Right? And you know that, of course, the normal operator has a minus sign. And they're unitary, right? If I multiply them, you get 1. That's how I know what the transpose is. We derive this. The transpose better multiply this to be equal to 1, so that's why you can figure out that's actually the complex conjugate. It just happened to come out that way, right? Okay, what's another way? How else can you turn this into that? Sorry, let me, I want to be a little cutesy here. Let's do that. How could I turn this into that? Huh? Yes, but give me a reason. Think Star Trek.
You go backwards in time?
Yeah, backward in time. If delta t is negative, then this turns into that. So what's happening is that this is going backward in time. So that is the eigenstate of the time revolving operator. Again, that doesn't mean things are going backward in time. It's just a math trick, right? And I just want to summarize what's happening with something that you want. I just don't think that this matters. There's no special meaning from it. One thing I do see sometimes I think is kind of cool is every now and then I'll see some stuff on cosmology and quarks and neutrinos. And it's like the neutrino, I think it's the neutrino, they thought is going the speed of light. And that was like weird for some reason, like it has mass or something, which is impossible. And so some people said it's going backward in time, or that antiparticles are actually normal particles that are simply going back in time. If any of you saw Tenet and could follow any of it, that's a miracle. The idea was that to make objects reverse, to travel backward in time, a person could travel backward in time, was you'd go through a machine that made entropy work in reverse. And if you think about that, the only way that could happen is if you travel backward in time. So that was clever. Unfortunately, the movie was far too complicated to follow. Because they had so what they did, and I have to talk about this is fascinating. Okay, forward in time I dropped that, but backward in time it would fly up in my hand. So all you had to do was do this, and then it would just pop up in your hand just like that if the object was being reversed in time. So that was kind of neat. You could follow that, but then they had all these action sequences, and I could not follow any of it because he had. I mean, did you see it right? He had like action sequences where one guy was fighting another guy, and one guy was going forward in time, the other guy was going backward in time. And I mean, it was cool, but it was completely confusing. Anyway, I don't know why I'm talking about that. Look, we're done with this. Again, please, if you haven't started on your homework, you're really screwing up at this point. If you haven't started on that, we'll have a review on Tuesday and maybe another one Thursday. So I guess we can dismiss. No, just kidding. All right, so I'm actually behind as usual. So now we're going to go. So there's two things. We're still going to do a little bit of time-dependent this or that with bonds. right? Remember the harmonic oscillator is a spring, but a spring is a representative of a chemical bond. It's a fairly decent way to start. You should have had it as an undergrad. It's in my silly textbook. I think it's in there. God, I better double check that. Remind me if it's not in there. Anyway, this is like an undergrad level. So what we're going to do with it is we're going to do time dependence on it, but we're also going to solve the wave functions. Now, let me just remind you that what a harmonic oscillator is. All these problems are defined by Hamiltonians, so that's not a big surprise. Although there is one thing already, which is that M is really the reduced mass. So, right, it's, you remember reduced mass, right? M1 plus M2 over, or M1 times M2 over M1 plus M2, or reverse, I forgot. I just Google it, and I actually need it. It bothers me that neat. That's a better beat. Okay, so this kind of sucks. It should be, the book should make it more clear that it's a reduced mass. It uses a different symbol traditionally. Now, one reason that it doesn't is heads up. This could also be an object, on a quantum mechanical object, on a parabola, on a parabolic potential surface. Again, the spring is, so is the bond, but there's actually a ton of things that are on parabolic potential surfaces for which the harmonic oscillator is the solution. It describes a lot of things, and as you get more advanced stuff, people often describe their phenomenon. They're like, oh, you know what, this is actually really close to a harmonic oscillator, so let's just use the harmonic oscillator. So that's one reason they're motivated to use mass, because reduced mass would only be applicable to a bond. You definitely have it as one identifiable A bonded to B, and reduced mass is what I just said. Okay, now so anyway, blah, blah, blah. And also, since we're learning from a physics textbook, they have to do it this way, which is what I see about half the time in chemistry textbooks. I'm personally very annoyed with this. 1/2 m angular frequency. Is that angular frequency squared? I thought that was squared.
Yeah, it is.
It is?
Yes.
I better double check that. Yeah, that doesn't look right to me. Yeah, that's in there? Oh, okay, I'll trust you. Yeah, okay. Remind me to change my notes. Anyway, so physicists like to do it this way. And again, I do see it put that way about half the time. Just, it's important for you to recognize, you know, the reason this is important is sometimes people will just say, oh, okay, here's a Hamiltonian. And you're like expected to recognize that as being a harmonic oscillator. So that's why that's important. Okay, of course, the angular frequency. Well, this is one thing that's kind of nice. The angular frequency is, you know, I've actually got this one memorized. I don't even need to Google that. That comes up enough that I remember that. The wave functions are what Hermite polynomials times e to the minus x squared. Of course, it's normalized. You can't have, there's units in front of the x to wipe out, to wipe out you can't have e to the minus meter squared. Anyway, we'll get into that. Energy is, so again, Hamiltonian, you saw it as an undergrad. Go look in an 18th century textbook, and you find the solution is basically bell curves, or bell curves times x or x squared. Hermite polynomials, and maybe you can look those up, Google or whatnot. Now, once you have the eigenvectors, you can then get the eigenvalues. Sorry, get the eigenvalues first, then you get the eigenvectors, and we'll find this relationship. So you have a principal quantum number. As usual, it's only a whole number. It likes to start with 0. Sometimes some people don't like that. And I hate it when I see this. It just drives me nuts because I don't know what I'm seeing. You see what they did there? See how clever that was? Right, if they change n from 1, 2, 3 like a particle in a box, then you can make that a minus. Anyway, God, it burns me up every time I see that. Just stick to something, right? Anyway, I prefer this. This is what you see in traditional chemistry, this, that. Okay. So what? So here's the thing. I'm not actually going to solve, we are going to solve the wave functions, but we're not going to just solve the wave functions. What I'm really going to do is introduce some new operators. And these operators are terribly important. You will see these the rest of your life if you're doing any kind of research in physical sciences, God forbid physical chemistry of some sort. You will see these forever. And these are called creation and annihilation. Let me start with annihilation. Annihilation operator, we call it A. So, got more stuff with A. M, frequency, 2H bar. X plus. So it's going to put two operators together. Now, the creation operator, by the way, I believe is the transpose. I'm pretty sure it is. That confuses me. Let me double check it. But the transpose of the annihilation is called the creation. And I'll look up a little bit more. Let me make sure that I'm not screwing that up. I don't think so. And as you can imagine, what could you do to the creation, sorry, the annihilation to make something new? Take a complex conjugate. That's something you can do quite obviously to make it like orthogonal to the. What's kind of neat is if you multiply them together, it's not a unitary operator. Annihilation and creation, these are not unitary, right? If you multiply these together, you're not going to get one. So why am I introducing, what are they? I'll show you. I mean, it's going to take a while. I guess we're going to spend most of the next lecture on this. This is a little unpleasant. But again, these are important. You will see these forever and ever and ever. They're not unitary operators. What they do, we're going to spend a very long time coming over the next lecture. But I do notice one thing. I noticed that I could do some algebraic manipulation to get just x and p. So what I could do, what I'm seeing here, I'm seeing a potential with these. I mean, it's really the same operator, right? It's just that's the transpose. But because of their properties, we actually give them different names for good reason. You'll see why. And it looks to me like I could write this. I can put these two together to get p squared out. I can put these two together to get position squared out. And it looks like I could write the Hamiltonian in terms of this. In fact, I will. And if I have the Hamiltonian in terms of this, then what I'm looking for is their eigenstates. And when I solve that, what I'm going to get is this thing right here. And then with that, then of course I get the energies and whatnot. So that's the idea. Okay. So I've got 5 minutes, which is a good thing because to review what these do takes a little bit more than an hour. So I've introduced them. Let me introduce as many properties of them as I can get, and then we're just going to go straight from there on Wednesday. And again, this will allow us to solve. We're going to solve the wave functions in a way that's very different than the standard Diffie cube. And more importantly, you're going to get really used to these things. Okay, so now, just like I was bemoaning the derivations where then you get halfway, you stop, you do a different derivation, and you put that part into the first derivation, and then maybe you do that again, right? You kind of start and stop with these all the time. I'm going to do the commutator just for the hell of it. Okay, let's do that. I mean, commutators keep coming up all the time, but of course I have a very specific reason to do this. It's going to be very important to figuring out what the eigenstates are and whatnot. Okay. So there's, if you don't mind if I just drop the little hat, oh, well, I'll try to, I can do that. Maybe you can't see them. So you can see I can factor it, I can make it a little bit nicer. Now I'm going to reverse that. And I'm going to factor this, I'm going to FOIL this out, but I'm going to do it real quick. I'm going to be real cheap about this, by the way. I'm assuming you can handle reasonably high-level algebra at this point. Okay, look at this, x squared. What am I going to get over here, x squared, except we got a minus sign? All right, what have I got? Minus I squared p plus p squared. So I got plus p squared, I've got plus p squared, oh, but there's a minus sign. Okay, the only thing that survives are cross terms. So that's my point. So I'm just going to go ahead and do all the stuff. And just, just trust me that this is what it comes down to. And obviously, we're going to have tons of commutators. Actually, it looks like the same commutator twice. And again, you're seeing x's and p's together because the x squareds and p squareds disappear. You factor minus I out, and what you end up with is, I just realized I shouldn't be using brackets. I need to be more careful about use of brackets, because here's a commutator, right? If I factor minus I out, then I've got xp minus px. And look at it, I got the same thing. So I've got two of these. Okay. That's IH bar, right? That's minus I squared H bar. That's IH bar, so I've got minus I squared H bar over H. What's that? 1, right? Okay. Now remember, one of the only thing that's actually easy in terms of a little handy-dandy whatever, the way commutators work, A minus B, then B minus A, of course, is minus that. So the, what's that? That's creation, that's annihilation. Minus 1, annihilation, creation, plus 1. Okay, so they do commute. They do not commute. Whatever, that actually is really not important. It does show you they're not unitary. What you can do, let's see if I can get this far, is, and this is going to be kind of nutty, is define the number operator. This is kind of nutty because it's the transpose operator. Now, again, you may think like, well, that's 1, right? No, it's not 1, it's not unitary. If it was a unitary operator, this would be 1, but it's not. So, what is it? Okay, now if you do a whole bunch of algebra, what you find is, and I'll stop here. Now remember that you have the definitions of these things, and so yeah, this is a little. This is it takes a little bit of algebra, a little foiling. Don't get those confused. This is updating. So you can see that there's this commutator here. This ends up being okay. So again, just I know that's just a slew of numbers that just got thrown at you. We'll stop here because look at this. I can now, therefore n plus 1/2. And let's multiply that by Hamiltonian. Does that look familiar? Oh, sorry, I had the H bar W on the wrong side. But there you go. So you can see what n needs a hat. You can see what n does. It's going to return the it's going to return the quantum number of the state, which, because I'm not a jerk, will either be 0, 1, 2, 3. It will not be 1, 2, 3, right? So now you see what n does. N is going to return the principal quantum number of the wave function state that's fed to it. It's related to this. And again, what we did was, in the big picture, the creation and annihilation, having x and p in it, we just simply manipulated them to essentially just return the Hamiltonian, which had x and p in it. Okay, from there, next time, we're going to be able to solve the wave functions in terms of the annihilation and creation operators. And then we're going to do time-dependent eyes, and that will be the rest of the week. And you will be unbelievable experts at the harmonic oscillator at that